Hello, everyone. Welcome to another edition of the Focus on Geothermal webinar series. This is a partnership between ThinkJ Energy and Enerchange. So I'm Carla from ThinkJ Energy, and today we have the distinct pleasure of hosting Kevin Jones from the U.S. Department of Energy Geothermal Technologies Office. So Kevin is the EGS Acting Program Manager as part of the FORGE project, or the Frontier Observatory for Research in Geothermal Energy. Kevin has a background in geology from the Indiana University and a PhD in geochemistry from Columbia University. As anyone who's followed geothermal news in, say, the past few years, the FORGE project is a project funded by the U.S. Department of Energy. It is an underground field laboratory for developing, testing, and accelerating technologies for enhanced geothermal systems, with the goal of accelerating the uptake of these technologies and the development of geothermal resources around the world. But of course, Kevin can explain this much better than I could. So, Kevin, the floor is yours.
Okay, thank you for the introduction, Carla. So let's jump into the presentation. So today I'm going to talk about FORGE, as Carla mentioned, the Frontier Observatory for Research in Geothermal Energy. And yes, I'm Kevin Jones, and I'm the EGS program manager as well as the DOE FORGE manager and strategy lead. And I'm with the Geothermal Technologies Office here in the United States. So here's the overall agenda. I'm going to walk through an overview and background on FORGE. We're going to talk about some drilling results and challenges, some stimulations that have occurred at FORGE, as well as future operations and some of the R&D solicitations, and just a little overview on the projects. But first, I'd like to thank Dr. Joe Moore, Dr. John McLennan, and the rest of the Utah FORGE team for all the outstanding work that they've done to date. Listen, I don't need to tell folks attending a geothermal webinar on a Friday that geothermal is having a moment, but it really is. The United States Department of Energy is making big investments in geothermal technologies. Startups are making and undertaking commercial scale developments. They're attracting lots of investment, and they're starting to make really exciting announcements, as well as hiring a lot of people. So it really feels like geothermal is having a moment, and it's truly a really exciting time for geothermal. And I think a big part of this moment is a direct result of the United States Department of Energy committing to funding this enhanced geothermal systems field laboratory called FORGE. And I think most importantly, I think a lot of that moment is also a direct result of the great successes that the FORGE team and their collaborators have achieved to date. So let's talk a little bit more about the tremendous work that's been undertaken at FORGE. So this is the Frontier Observatory for Research in Geothermal Energy, or FORGE. It's by far GTO's largest funding initiative, and is enabled by more than $215 million in federal investment and decades of public and private research. So as you look to the right, you can see a map of the state of Utah. The FORGE site is close to the town of Milford, which is about 3 hours, a little more than 3 hours drive south of Salt Lake City. And the state of Utah is in the American West. And then the map, the upper right panel, shows a map of the FORGE site, as well as the locations of some of the wells. And the FORGE site is located within the Milford Valley and in what they call the Milford Renewable Energy Corridor. So there's an existing geothermal power plant that takes advantage of a natural hydrothermal system. There's also a wind turbine, or a wind farm that has a 300 megawatt wind farm, and a solar farm. And there's even a hog farm nearby that they use, the waste is used to produce biogas. So forge is situated in a very interesting area. And the forge site is meant to be a dedicated site where scientists and engineers can develop, test, and accelerate breakthroughs in enhanced geothermal systems, technologies, and techniques. And some of the goals of Forge are to enable research, geothermal research and EGS research in a broad range of technologies. And it's meant to allow scientists to identify a replicable commercial pathway to enhance geothermal systems. And one of the great aspects of Forge that I'm really proud of is the amount of data that the Forge team has collected, and that all that data is available in real time. So folks here can go to the geothermal data repository. They can view the Forge wiki. They can get a very good overview of all of the wells and all of the work that has been done at Forge, as well as all the R&D projects. And you can actually download data. There are links to data sets on GDR that you can download and you can look at, you can analyze. So it's a really tremendous thing that the Forge team has done there. Now, just a little bit of background on how the Forge funding opportunity was designed. So it was meant to be a competitive process to identify the optimal EGS test site. And that FOA was released, that funding opportunity, or FOA, was released in 2014. And there were initially 5 different locations that all were evaluated. And then there was a down selection to 2 sites. And one of those sites was the Utah Forge site. Another one was the Utah, Forge Fallon site. And then there were a series of go, no goes. And at the very end, there was a final down select, and the Utah Forge team moved into phase 3, or the implementation phase, and that's large scale drilling of full scale wells, stimulations, and flow testing. And one of the key aspects of some of these down selects and these go no goes were related to seismic monitoring. Seismic monitoring is something that the United States Department of Energy understood could be a concern related to enhanced geothermal systems. So it was something that we spent a lot of time considering, analyzing. So one thing for sure, the United States Department of Energy is not willing to compromise on the safety of these sites. So we've paid a lot of attention to induced seismicity and other issues. At the current time, Forge is nearing the end of their implementation phase. And right now, Utah Forge and the United States Department of Energy are currently in negotiations to extend the project as authorized by the Energy Act of 2020. So a little overview on the geologic setting at Forge. There's about 3,000 to 5,000 feet of alluvium overlying the granitoid EGS reservoir at Forge. And the site is adjacent, as I mentioned, to the Blundell geothermal power plant. So you can see a geologic map with the Utah Forge site. And then below you can see a cross section. So you can see the alluvium on the left, upper left, as well as the granitoid reservoir in green that takes up most of the cross section panel. And then there's a key geologic feature called the Opal Mound Fault. To the east of this fault, you have the Roosevelt hydrothermal system, Roosevelt Hot Springs hydrothermal system, and you can see a convective geothermal gradient, and the power plant takes advantage of that convective system. And then to the west of the fault, you have no observed faulting at the surface. You've got very little fractures. It's very low permeability. But also in a conductive geothermal gradient, which makes it sort of an ideal location for an enhanced geothermal system. So there's no fluid, there's no known fractures or faulting. So this is a place where we can go in and we can create the fractures to create a human-made geothermal system. Excuse me. So the Forge site currently has 7 wells drilled. Those include one injector, the 16A well, one producer, the 16B well, as well as several seismic monitoring wells. You can see in the lower right-hand panel is a temperature profile for several wells, and the bottom hole temperature at around 8 to 9,000 feet, or about 2,500 meters depth, is a temperature of about 225 degrees C. One other interesting aspect of the area is that the Fervo recently broke ground on a commercial EGS site, what they're calling 400 megawatt commercial EGS site immediately adjacent to the Forge project. So a lot of the site characterization work that was done by Forge likely is helping and contributing to that project. Now, one of the most outstanding results that Forge was able to make, in the successes that they've had, was related to drilling. So the upper right-hand panel shows a progression of wells. So the one in blue to the right. So this is days on bottom hour drilling hours versus depth curve. So the blue well, all the way on the upper right, was drilled with a rock bit, and they drilled to around 7,200 feet, and it took 20 days of just on bottom drilling to get to that 7,200 feet. And then what happened was GTO, the United States Department of Energy, promoted a collaboration between Texas A&M University, who had a project with GTO for the efficient drilling for geothermal energy FOA, or EDGE, and they collaborated with Forge to find drilling enhancements and drilling hard granitoid rock. So once they got involved with the project, you saw marked improvements in drilling rates. So this is the first well in red, the second well, vertical well in orange, and then the third and fourth wells. So these results were a direct impact of getting Fred DePriest and Sam Neunier at Texas A&M involved in this project. And what they did is they used polycrystalline diamond compact bits, and there was sort of a bias in the geothermal field against these bits because they said they tended not to work, or they got damaged too quickly. But what we were able to do is we were able to utilize those bits and have people that really knew how to use them, and combine that with their physics-based limiter redesign workflow, and they were able to make these tremendous improvements. So instantaneous rates of penetration were around 250 feet per hour, but those weren't really achieved. You saw a rapid drop-off from 250 feet per hour to around 70 feet per hour within the first couple hundred feet of drilling. So that's one thing, and that was on the 78B well, which is the third well, and that's one of the things that the Forge team wanted to evaluate when drilling 16B. So they designed a drilling plan that would allow them to understand the cause of this, and then look for this and other limitations on Forge drilling, so that those limitations can be mitigated. So this is a little bit of information on results from that drilling plan. So we were able to gain some insights to the ROP drop at Forge. They were able to pull bits early to observe any changes to the cutters during drilling. And what they found is that the wear flats that occur on these cutters best correlated with the drop in ROP. So this ROP was consistent with increased friction due to cutter chamfering. And they also tested more aggressive cutters. So you can see on the lower right here, you've got these interesting letters to see if those improved the drilling rates. And they did find the higher sustained ROPs. So that shows the potential for maintaining those sustaining those higher ROPs at Forge and other hard rock. And this has impact to other locations. For example, Provost project next door are obviously benefiting from the research that has occurred at Forge related to drilling. And then this physics-based process, limiter redesign process, is also being applied at the project at the geysers in California. So we've had tremendous success at Forge to improve drilling rates, but drilling rates can only decrease the cost of a well so far. You could drill in an instant and you'd still have to pay a lot of money for casing and cement and other costs. So we've made significant progress in drilling. There's still more progress to be made, but we also need to focus on further reductions to well costs through reduced materials costs, through more efficient well designs, or by other means. Another interesting aspect of some of the Forge wells is that the logs that were run after the well was drilled revealed significant borehole rugosity. So they observed a lot of these ledges and patterns that were caused by the drilling tool, as well as the way that the tools were being run. And these boreholes, the rugosity presents a significant challenge. So they create these ledges that are a hazard to fiber optic cable deployment. And given the temperature constraints at Forge, most geophones can't survive at the reservoir temperatures that Forge that occur at Forge. So fiber optic cable is one of the main ways that we can monitor seismicity at the reservoir. So the ability to run fiber optic cable successfully is absolutely critical. So the Utah Forge team and the Texas A&M team developed a plan to minimize this borehole rugosity to make sure that we had the best chance of running fiber optic cable in the future. And they did that by, they tested a rotary steerable system, they used longer gauge bits, and they also tested adjustments to drilling practices to reduce this borehole rugosity. And then here's some of the results. So basically the practices that they implemented largely eliminated any ledging and borehole rugosity, these patterns that they were observing in the wells. And they only observed really one micro dog leg in the well. So what this led to was the successful deployment of fiber optic cable in 16B, which was absolutely critical monitoring infrastructure for the stimulations as well as the flow testing. So that was incredibly exciting. And then on the right, you can see the fiber deployment operations. We deployed 3 fiber optic cables, 2 DSS, DTS, and DAS cables, as well as 1 fiber optic pressure temperature gauge. So very complex fiber optic running operations that were ultimately successful. Now, just a little bit of overview on the first simulation at Forge. So the Forge team conducted a simulation on 16A to guide the location of the 16B well, the producer well. So they conducted 3 stages of simulation using slick water and a viscosified fluid. And for the first simulations, they didn't use any proppant. And what they did is they stimulated the well, they observed the seismic cloud, and that helped guide the location of 16B, which was meant to intersect that seismic cloud. So the upper left-hand corner shows the seismicity with time for each of the 3 stages. And you can see the resulting seismic cloud. One issue related to the seismic data is that we had tremendous problems with the geophones that were used to monitor the seismicity. So those failed fairly rapidly. So the first simulation, we only had one geophone array in place that was active and functional. By the second simulation, we were able to get another one in the ground, and then by the third simulation, we were able to get a third. So this definitely revealed a significant challenge with respect to in-reservoir seismic monitoring. So after the simulation, the Forge team conducted some initial flow tests to try to evaluate the connections, and we identified that there definitely was a connection established, but it required high injection pressure. So the injection rate was, we were able to achieve close to nearly 8 barrels per minute of injection rate. But the connection was there, but it was quite minimal. So the rate that was out of the producer is measured here in barrels per hour. So a significant reduction in the connection was quite limited. So this led to some key findings. One, we definitely did establish a connection. Two, proppant and probably larger stimulation volumes are likely necessary to improve the connections in future simulations. And the seismicity likely overestimates the domain of stimulating fractures. You can see in the upper left-hand corner, there's a lot of seismic activity related to the simulation, but that didn't translate to a lot of open fracture pathways for fluid. This is a little bit of overview on the challenges that we've had with geophones at Forge. So the geophones were deployed in one of the seismic monitoring wells just a couple of weeks or a week before October 13th, 2022, fully functional. And then within a week, most of those geophones failed. So you can see at the top, this is the near surface geophone that represents the expected signal, and then this is what you're observing at depth. So 2 of the 3 components were not functional after only a week, and only the horizontal 2 component was still functional at 150 degrees Celsius, and then at 170, all of them were reading noise, and then only slightly less than a week later, everything had completely failed. So this just told us that the current technology really struggles to operate even at moderate geothermal temperatures. This isn't even close to the full reservoir temperature at Forge, or the bottom hole temperature at Forge of 225 C. So one of the things that GTO is doing to try to mitigate this issue is we've invested a significant amount of money into funding the Geothermal Geophone Prize, which is incentivizing the development of high temperature seismic sensors that can operate at geothermal temperatures up to 250 degrees Celsius. So right now, so the prize offered $3.65 million in cash and vouchers to work with DOE national laboratories to develop these seismic sensors. And there are currently 5 teams selected for phase 3, which includes the development of prototypes as well as lab testing. And then at the end of the process, 2 of these 5 teams will be selected as prize winners, and we will deploy their seismic sensors in the field, potentially at Forge or at another high temperature location. So this is, it's basically one of the things that GTO does, is we identify needs in geothermal technologies, R&D needs, and we fund opportunities to meet those needs. Now, here's an update. So we talked about the first Forge simulation. There was a second simulation in April of this year. The Forge team pumped 13 stages, varying from single cluster stages up to 8 clusters per stage. The upper right-hand panel shows just a view of the well bores. You can see open hole sections at depth, and then you can see the stages that were pumped in the 16A, the injector well in blue, and then as well as the stages that were pumped in the 16B well, the red well. So we varied fluid type, proppant volumes, as well as tested an ultra lightweight proppant. And we had some significant success. So most stages treated really well. They took significant fluid and proppant volumes, and most of the stages in 16B showed some rapid pressure drops. So the operation basically went like this: we stimulated 16A. Since we had functional fiber in 16B, we were able to monitor for fracture hits on the 16B well, and then we went in and we stimulated the 16B well in the locations where those fractures hit. And once we began stimulating 16B well, we typically would observe this rapid pressure drop early on in the stimulation treatment, and a drop of 1,000 psi over a very short period of time. And we think that's the fractures that are being generated in the 16B well connecting to those fractures that were pumped in the 16A well and making a really strong connection. We also observed a challenge. There was a couple of stages or a few stages that were attempted, and we just weren't able to establish a significant injection rate. We don't quite know the reason for this at the moment, but it's being analyzed. But the 6A, the 6B, and the stage 7 in the 16A all had this same significant challenge. So in summary, stimulating both wells is likely necessary. We don't think we would have had that connection between the two wells had we not stimulated the 16B well in the way that we did. Also, prediction of tight sections could be a critical process for future efficient operations. And then, we pumped a lot of proppant, and in the future, the silica sand is good for oil and gas operations, but it may not be appropriate for geothermal operations. So we may need high temperature proppant. And that's one of the things that's being researched at Forge or by Forge subawards that I'll talk a little bit about in the future in just a little bit. And then after that stimulation, there was some additional flow testing. So this was a 9-hour flow test, and it evaluated the connection established between these two wells, and that we saw significant improvement in the discharge rate from 16B as a result of this stimulation versus the previous stimulation. So in this stimulation, we're injecting around 13 barrels per minute, and we're seeing outflow at 8+ barrels per minute. And you can see in purple here the discharge rate that it's actually rising. Some modeling that the Forge team has performed suggests that this discharge rate is going to asymptotically approach the injection rate over the course of more than 30 days. But the rates were drastically improved, 8+ barrels per minute versus less than a barrel per minute, and after the first stimulation. And this flow testing informed the plans for longer term flow testing, approximately 30 days, that the Forge team is undertaking right now. All right, so some background on future operations at Forge. So as I just mentioned, the 30-day flow test started earlier this month, and it's going to provide a significant amount of data on the heat extraction process and its efficiency here at Forge. And it's going to give insights to potential future operations. And the flow testing is going to including tracers, geochemical sampling, seismic monitoring. So there's going to be a lot of data gathered, as well as monitoring the fiber optic cable. Now, unfortunately, we just found out about a week ago, as the well bore heated up as you're flowing out of the 16B well, we actually, the fiber optic cable, connection to the fiber optic cable was lost. We're also considering an extension of the Forge project that I mentioned earlier that was authorized by the United States Congress and signed into law by the president. And the extension of scope and budget is currently being negotiated. But the kinds of operations that we would envision for Forge in the future include, drilling of another well or wells, as well as to test larger spacing or to perform operations at higher temperatures, or as just infrastructure to test high temperature tools that are being developed by Forge R&D. And then there's also we're also likely to perform additional simulations. So in the previous slide that talked about simulations, we've only utilized a fraction of the 2 wells that we've already drilled at this point. So there's still more simulations to test in those wells, and there could be, and those simulation tests on those wells could inform a simulation on a future well. I alluded to Forge R&D. So Forge also manages research external R&D. The first Forge solicitation had 17 selections, 17 R&D projects, and for a combined total funding of 49 million. And those were spread over several topic areas, including devices suitable for zonal isolation at high temperature, estimation of stress parameters, the field scale characterization of THMC modeling, stimulation configuration of the wells at Forge, and as well as integrated laboratory studies for THMC processes. And then there was a second Forge solicitation, and these projects are managed by the Forge team as subawards, and DOE contributes to the monitoring and evaluation of those projects. In the second solicitation, 13 projects were selected for a combined total funding of 44 million, and those are spread across 5 different topics: adaptive induced seismicity monitoring protocols, alternative stimulation schemes, field scale experiments for heat sweep efficiency, high temperature proppants, which I mentioned a little bit ago. And topic 5 is to develop a high temperature multi-set straddle packer for open hole operations in geothermal. Okay, so that's the talk, but I just want to mention just talk briefly about how to engage with GTO. We've got a lot of tools and resources to help spread the word about geothermal energy and engage with our stakeholders. We do funding opportunities. We've got great websites that folks should take a look at. We also produce these quick guides for funding opportunities. We've got a monthly newsletter email blast, the drill down that folks can sign up for. We've produced a lithium story map and other communications products to help folks understand the work that's going on here at DOE. So please engage with us. We'd love to engage with our stakeholder community. So thank you. Once again, if you're not already signed up for the drill down, our monthly newsletter. And if you're interested in serving as a merit reviewer, so one of the key things that we need in DOE is we need independent reviewers to evaluate R&D projects. So independent reviewers would have been used to evaluate the Forge project, for example, or other EGS demonstration projects. And we really value the independent view of scientists that are knowledgeable of geothermal. So if you are interested, please submit your resume to the website that you see on the screen. And we'll leave it at that. Thank you.
Hey, thank you, Kevin. That was a lot. And so we've been following the Utah Forge project for a really long time, and it's quite impressive and also very interesting that beyond trying to prove the viability of EGS as a geothermal system, you're also developing these technologies that will inevitably cascade to other geothermal projects around the world. So we have a lot of questions coming in right now. For everyone else who's still in the webinar, you can send in your questions. There's a questions tab there, and we'll try to get to all of these. We have a lot. Okay, first things first. For those asking if the slide pack or the presentation will be made available, we will be uploading the recording of the webinar in our YouTube channel. So that's the Think J Energy YouTube channels. Just wait a couple of days and it'll be up there. We have a couple of very, very specific questions on drilling. So let's see if we can go through them very quickly. Kevin, can you give us an average UCS value of the granite in the site that is being drilled?
No, not off the top of my head. That's Yeah, I think all of that data. So several of the images that I shared during the drilling section cite a manuscript by Fred and Sam, SPE IADC manuscript. So that paper should have a lot of these detailed. So I'm not a drilling engineer. I didn't perform the research, but all that information should be out there in those manuscripts. So folks that have very specific questions on drilling, I'd invite you to read those papers and potentially engage with the authors.
Yeah, I mean the great thing about Forge is that all of the data you're producing is publicly available. So if anyone in the audience has very specific figures or numbers that you're looking for, we encourage looking into their Forge wiki or the GDR website, correct?
Correct.
Okay, then we have a bunch of questions here relating to fiber optics and geophones. Quick question. Please explain what are DSS and DAS cables. These are types of fiber optic cables, correct?
Sorry, I didn't catch that.
Sorry, please explain what are DSS and DAS cables.
I think strain sensing and acoustic sensing cables.
Okay. Yeah, yeah. Okay, got it. So there's a question here about the failure of the geophones. Um, do you expect that fiber optic technology can be part of the solution to this problem?
Absolutely. Several of the teams that have advanced to phase 3 of the prize have fiber optic solutions to this issue. So we absolutely think that fiber optics is one of the ways that we can get reservoir level seismic monitoring continuous and uh, for over long periods of time. One thing about the acoustic fibers is that they don't have 3-component geophones, so they're single mode. So we're really looking for those 3-component geophones, and that's what all of those projects are creating. So we absolutely did have acoustic fiber operating during the the second simulation that occurred earlier this year. We got great data thanks in part to the deep fiber that we had available in the 16B well.
You
So
mentioned that
absolutely,
there was
fiber is going to be a key part of this. Sorry, go ahead, Carla.
Sorry, yeah, I got it. You mentioned that in your current flow test, you had a failure of a fiber optic cable. So there's a question that's curious about the type of failure. So was it a failure of the connector? Was it a failure of the fiber itself? Did it fail in the lower section of the well?
We don't know exactly the reason for the failure, but I think it occurred at around 4,800 feet. So the total MD of the 16B well is very close to 11,000 feet. And the kickoff to the tangent section, the inclined section of the well, I think it's around 6,000 feet. So somewhere in the vertical section, the fiber was severed, and we lost connection to everything below that point. So we still have some functional fiber. It's just shallow in the well. So we're still using it for monitoring seismic activity. So it's still useful for that. But we were getting a temperature profile all along that fiber with the DTS fiber. And unfortunately, we've lost that as well as the strain and deep acoustic.
When can we expect the detailed report on the flow test that you're currently doing?
That's a good question. So Forge produces uh, reports almost on a yearly basis. So there are several reports that are available that cover a lot of the operations that we talked about. There are also write papers and submit papers to the Stanford Geothermal Workshop as well as geothermal rising. So there's a lot of information out there. There's also papers in other journals as well. So a lot of this information is out there. Uh, and then on GDR, on the Geothermal Data Repository that folks can look up, there also are various reports. I would expect the reports on these latest operations to occur sometime after October. So I can't say exactly when. It could be by the end of the year, or it could follow after that. But once this flow test is completed, that essentially completed the original scope of the Forge project. And so I would expect a detailed report covering the entire project to follow after that.
Okay, looking forward to it. Another question here on seismic monitoring. Is there a seismic limit at which you must stop your drilling and stimulation operations? Are the limits defined by federal or state regulations, or are these set by Utah Forge?
These are set by Utah Forge and the United States Department of Energy. So we've identified um, thresholds for them to reduce injection as well as and I think when we currently are using what we call a traffic light system. So green means go, yellow means um, slow down and be careful, and then red means stop. And anything above a 2 is where we say, okay, slow down. Anything above a magnitude 3, which is probably barely sensible or not even sensible at the surface, we say stop and let's take a closer look at this. But fortunately, through all of these operations, stimulation, the um, the flow testing that's currently ongoing for multiple days, weeks at this point, has never produced anything close to a magnitude 3.
Hmm, okay, that's great. And a bunch of questions here related to drilling and stimulation. Fairly basic one. How did you achieve the zonal isolation for the stimulation operations?
It was just cased and cemented, and then it was a plug and perf operation for the second stimulation.
Were there any losses during drilling? I guess it is particularly applicable for the second well, the production well.
No, there were no losses. We definitely did observe. I believe we observed pressure on the 16A while we were drilling, but there have never been any losses of note during the drilling of any of these wells.
Okay. What was the limit that you set between the distance between bottom holes of 16A and 16B?
So the tangent sections of 16A and 16B are approximately 300 feet or 100 meters apart.
For the next, you mentioned that you have plans of drilling other wells. So are you going to try to space that out farther?
So that's one of the ideas. The project's still in the potential extension is still in negotiation. It's not something that is guaranteed to happen quite yet. But there's a number of things that we could test. We could test. We could move off to the side of the well. We could go deeper and try to make a connection over a larger distance. There are a number of potential options that we could consider, and we would be taking advice from, or recommendations, I should say, from the Utah Ports team, as well as there's the Science and Technology Analysis Team. This is a team of experts with a lot of industry experience in either geothermal or industry and academic experience in either geothermal or oil and gas, and they would also likely make recommendations on what should be a goal for Forge in the event of an extension. So a lot of different potential pathways. We haven't landed on exactly what would be the right approach, but first we've got to negotiate and get that extension in place with the Utah Forge team.
Okay, then. Are there plans to test alternative working fluids for the system? Are there also plans to use the system for, say, geological storage or flexible operations?
Um, so no plans currently for alternative working fluids, and then no plans. So I mean, I think we could obviously do tests to evaluate thermal energy storage and flexible operations. I think that is absolutely within the realm of tests that Forge could run under an extension. But the main focus of the initial phase was really to get what we are calling like a month-long flow test to understand heat extraction of the system and just the efficiency of the system. But there's a number of different tests that we could undertake in the event of an extension.
Okay. We have a couple of questions again asking for very specific figures. So they're asking for surface pressures observed while fracturing, during stimulation, and if is there a measurement for geothermal gradient within the granites. I believe this data should be available publicly.
Yes, absolutely. The injection, the pressures observed at surface during the pumping is, I don't know if those are public quite yet. I don't know if they've been uploaded to the GDR, but the wellheads are rated to 10,000 psi, and I think we kept it uh, below 8,000 for the most part. I think the maximum pressure might have gone a little bit higher than that, but I think we were looking at 10,000 psi minus a safety factor. And then, yeah, I'm not exactly sure what the geothermal gradient is at Forge, but yes, it's absolutely there. And we could probably go back to that previous slide and you could calculate it.
Okay, we have a series of interesting questions here coming in from Taiwan, which of course is a volcanic region for geothermal. So, what can you say about the techniques developed in Utah Forge and how these can be applied in volcanic areas? Do you think that is there any conclusion to how far an EGS system should be positioned away from existing fault lines?
What was the last addition? What existing what lines?
Sorry, existing fault lines.
Fault lines. Oh, yeah. I think you definitely want to stay away from faults because basically enhanced geothermal system, if you've got sufficient, enhanced geothermal systems are really designed in places where there aren't faults, there aren't natural fractures. It's all about creating a geothermal system where there was none. So you definitely want to be away from significant natural permeability. I don't know exactly what that standoff would be. At the Utah Forge site, there's no mapped fault at the surface, at least um, in the Utah Forge area, and as a result, we can cite several lines of evidence that there's not significant faulting in the reservoir below. There wasn't significant losses during drilling. Uh, During the initial stimulation, there wasn't a whole lot of, even after we fractured the rock, there wasn't a whole lot of permeability until we propped those fractures. So, there's a lot of evidence that there's very minimal natural fracture or none, effectively zero fracture porosity in the system. But if you're looking to implement a geothermal system, an enhanced geothermal system, you want to stay away from faulting, so that because those could be areas where you've got swarms of fractures, existing natural permeability that could take fluid away from the goal is to get the fluid to go from the injector to producer. You don't want a whole lot of natural permeability off to the side that is connected to your injector or producer that could siphon that injected fluid away.
A very interesting question here. How effectively is Forge utilizing deep drilling experience and skills from oil and gas?
Very effectively. I think the improvement in drilling is a direct result of the collaboration between experts in oil and gas and the Utah Forge. So Fred Dupriest and Sam Neunier, that Fred was a chief drilling engineer at ExxonMobil for a long time. So he essentially designed this limiter redesign process. He came up with it in collaboration with others, and this process of limiter redesign is kind of standard operating procedure within the oil field. So this is not something that had been widely deployed in geothermal before Fred and Sam were involved in the picture. But once they were, that's how we saw these drastic improvements in drilling. And you know, we are maybe not quite there with respect to matching the drilling rates that are observed in oil and gas, for example, in shale oil and shale gas regions, but we're getting close. And I think the work that Fred and Sam have done in collaboration with Utah Forge has really set us on a path to getting us to a place where we are matching those drilling rates.
Going back to drilling, there's a question here about whether Forge worked with a specific bit manufacturer to modify the bit based on the learnings that you got. So
Yes.
were these highly customized bits or were these off-the-shelf solutions?
I think they had to be somewhat off the shelf, but they were likely within because they were changing bits rapidly. So NOV was the company that they used for the 78B well, where we saw those, I think was the last vertical well where we were seeing um, really great drilling rates. So yes, they were absolutely working with NOV to modify bits on the to deploy different bits on the fly and making decisions about what bits to run as a result of that. So absolutely, they had there was great collaboration. And I think yeah, great collaboration with the bit manufacturer.
Okay, we're going back again to the fiber optics and how these can be optimized for high temperature systems. Given the failure that just happened recently during the flow test, do you have risk mitigation plans for the next time that you have to run a fiber optic sensor?
Um, I think this is all kind of hot off the press, so we don't we haven't performed an evaluation of exactly why the fiber failed to then create a mitigation for it. But absolutely, there's going to be a deep dive into the data to try to understand um, what are the possible reasons that the fiber failed. Now, what I'll say is that it would have been great to have the fiber continuously throughout the flow test, and it would have been great to have it in perpetuity, of course. Um, but I think the real advantage was during the stimulation. We definitely needed it during the stimulation. We definitely needed it to see where the fractures that were created in 16B, where they were connecting, or 16A were connecting to the 16B. So how are these wells connected? Well, what we found is that the the seismic the microseismic cloud is not necessarily reflective of the fracture pathways that are actually making the connections between these wells. So um, it's unfortunate that we lost the fiber. Absolutely, it's unfortunate, but we definitely had it when we absolutely needed it, and we definitely had it during the early phases of the flow test. So we got some really great data. So we will look for mitigations, but we're really happy about the results that we're able to get, even having the fiber for the time that we did.
You mentioned something that I find very interesting. During the second stimulation that you did in both wells, you said that you identified tight sections that did not respond to stimulation. So were these tight sections within the original seismic cloud that you mapped?
So the original seismic cloud was, so there were two simulations. The first simulation was down
Sorry, Kevin, your audio is dropping
hole
out.
from all of the second stimulation sites. So the seismic cloud that was generated from oh, sorry, it's telling me my audio might have cut out. Carlo, did you get that
Yeah,
entire answer?
yeah. I think we completely missed it. Hi, Kevin. Are you here?
Sorry. Yes, yes, I can hear you. Can you hear me?
Okay. Yeah, yeah. It's good now.
Okay, did you catch the entire answer to that question?
No, we didn't catch anything actually.
Okay, let me go again. So the seismic cloud that was originally mapped was from the first stimulation, and that is actually downhole from those tight sections that we observed. So no, I don't think there's any overlap to the original seismic cloud and those tight sections.
Okay, got it. So we just have a couple of comments here, particularly from Switzerland, from Nico Lupi. So they are very much looking forward to the achievements of Forge, and they are very appreciative of what you've discovered so far. And we know that these techniques are also now being tested in Switzerland, although perhaps to a different degree. And so we have a lot of people who are looking forward to your plans, your more results. So yeah, I think the industry is very optimistic.
So I would just like to take a moment to thank the folks at Geoenergy Suisse for the collaboration that they've taken with Forge. I didn't put it in the slide. I recognize that as an oversight on my part, but the Geoenergy Suisse folks have been absolutely critical, and that collaboration with them has been absolutely critical for seismic monitoring and getting detailed, precise locations and magnitudes of these events. So, gosh, I am sorry that I didn't give more credit to the Swiss because um, their work has been absolutely critical. So I'm really excited to see what how, how Switzerland uh, uses the results from Forge to implement their own enhanced geothermal systems. I really excited and wish them the best.
Yeah, we're all looking forward to the results. I think that's a good point as any to finish up the webinar. Thank you again, Kevin, for doing this so early in your time zone.
Got it. Thank you, Carlo, and thanks to everybody for attending. I hope you enjoyed it.
Thanks, everyone. Have a happy weekend.